What's up, dudes? I want to walk you through a few examples of typical spring problems. Here's one about a ball hung from a spring. We're given the spring's natural length. Ball hangs at equilibrium, blah, blah, blah. Find the spring constant. A question like this, I would start with a free body diagram. And we know the following. Spring force, or FEL, it's an equilibrium. What the tendency for people here is to like draw this. Don't do that. Don't draw the spring as if just draw the force that the spring applies. Okay. And then, well, if it's at equilibrium, we can say that. I'll sort of skip a step to here if you're okay with that. Find the spring's constant. Well, the spring force is Kx. All right. Now, remember, we said that spring force, we said is negative Kx, but that's when we are really considering the fact that, right, normally the spring is like by itself up here, and then we hang a mass from it, and it's what's the word I'm looking for? Displaced that way, right? Notice, displaced this way, but the spring force is upward. So, yes, that tells us about the direction of those two quantities, but as we said, don't worry about the negative mathematically. You won't use it. It refers to direction. So K is mg over x. K is, let's call it 65 newtons over, now x. X, how far the string has been stretched or compressed. Notice, natural length 1 meter, stretched to a length of 1.2 meters. Follow? The spring has been stretched 0.2 meters. So that's 325, right? Newtons per meter. Man, I never remember if K is in newtons per meter or newton meters. It's written right there. That's how you know. Okay? For B, okay, I'd start with the no, I wouldn't. I wouldn't start with any diagram. I'd start with my brain. And my brain says if an additional identical ball is hung from this thing, that means we're going to make this twice as big, which means we're going to make that twice as big, which means we're going to make this twice as big. If the spring has to pull twice as hard, that's because the spring is stretched twice as far. So in B, I know the new x is 0.4 meters. But that's not the question. The question is, what's the spring's new length? Well, its natural length is 1 meter. It's stretched 0.4 meters. The new length is 1.4 meters. You could just do this and say x is mg over k, and now, well, if there's two 6.5 kilogram balls, they would weigh 130 newtons divided by your 325 newtons per meter, and that'll give you your x is 0.4 meters. That'll lead you back there. But I don't think the math is necessary if you think carefully about how springs behave. Okay? Okay. An archer pulls a bowstring, her bowstring back 40 centimeters by exerting a force that increases uniformly from 0 up to 230 newtons. Right? As we hopefully are getting more comfortable with, here's the string. Right? Well, to pull the string, I wish there was a way to, never mind. To pull the string a tiny little bit so that the bow, so to make the string do that, that's not a good representation of it, but you know what I mean? To just start pulling it back, it hardly takes any force at all. And it takes more force to get it like that, because really what's happening is you're deflecting the bow more and more, right? And eventually the bow looks like that because the string is way back like this. All right, so it takes more force to pull it back farther and farther. All right, but to get it that far back takes that much force. What's the equivalent spring constant of the bow? Well, here, I mean, it's really just Kx. I think that's something like 500 and, what is it? 575. Okay? In B, which work does the archer do in pulling the bow? That's where I would start. We're given something about force, and D here is the same as X. How far the string is, how far that force is applied through. The distance that force is applied through. Now, what force is applied? Well, here's the deal. It's not a 230 Newton force the whole time, right? The force increases from 0 to 230. So here's where we do have to use the average force. It's a non-constant force. Okay? That can be tricky. How do you know whether to use the average force or not? Well, here's the deal. This is kind of an instantaneous, almost, if you look at it in that sort of way, value. To get it stretched that far, that's exactly how much force is required. If you pulled with any less force, you'd have to have a smaller x. If you pulled any harder, you'd stretch it more than that. So K is a ratio of, how hard do you have to pull to get it to stretch or compress a certain amount. All right, so don't use the average there. Because, K is almost really like finding a data point on that graph. Okay? But when we do when we do work, we're saying that the force is applied as something moves a certain distance. And as we said before, the string looks like this, and then like this, and then like this. Well, as we pull a little bit, and a little bit harder, and a little bit harder, well, there's a non-constant force, so that's why we have to take the average here. Okay? Okay, and part C says a 100-gram arrow is put in the bow, pulled back 0.55 meters, and released. What's the arrow's initial acceleration? So here's the dealio. We got, here's the bow, here's the string, here's the arrow. In order to look, for the whole shebang to look like that, we'd have to have a force that we are applying, and therefore, what stinks is this is not supposed to be a vector. It's supposed to be the actual arrow. So if we draw a free body diagram for the arrow, it looks like this. Well, the arrow is being pushed this way by a spring force. And we're pulling, well, you know what? Yeah, sure, we're pulling back. But the question is, when this thing is released. So when we release it, we're not pulling it back anymore. And there's all we have. So of course, when we get rid of this pulling back force, what we get is an unbalanced force that way. And we can say that the spring force equals ma, or that kx equals ma, or that a is kx over m. And guess what? It doesn't matter how far you pull the spring, k is constant. Excuse me. All right, K is just a ratio of how much force it takes to stretch a certain distance, or force per unit distance. All right, and that's a constant for what we call a linear spring. Until you pull it so hard that you deform it and it doesn't act like a spring anymore, we're going to assume that we don't do that. Okay? So we stick with the 575 newtons per meter times this new distance we've pulled it back divided by the 100 grams, but we got to put it in kilograms. Yeah? And, oh boy, I don't know what that is. How do I know? 575 times 0.55 divided by 0.1. Whoa! 3,162 meters per second squared. Whew. That's accelerating like crazy. Now, it doesn't do that the whole time, and that's why if you look carefully at the phrasing of the question, what's the arrow's initial acceleration? Right? Because it accelerates that fast when x is a certain value and the force is a certain value. But as soon as the spring, or the bow in this case, which acts like a spring, starts to go back towards its original setup, x gets smaller, f gets smaller, and acceleration gets smaller until f gets smaller, until it's supposed to go all the way back to 0. Eventually, when x is back to its initial, or the spring is back to its initial length, or the bow in this case is back to its initial whatever, there's no more force, and the thing doesn't accelerate anymore. So the deal is it speeds up the whole time, the arrow does, but the rate at which it speeds up decreases. So it looks something like this. You get me? It keeps getting faster, but the rate at which it keeps getting faster slows down. Tricky, but neat. Okay? Okay, now the pretty involved one. All right, as we said, as you've heard me say, the forces that springs exert are conservative forces. As long as we neglect things like, if you take a spring and stretch it, stretch it and let it back, stretch it and let it back, stretch it and let it back, stretch it and let it back. Eventually the spring will heat up. Let's neglect that, all right? And so we say that, yeah, spring forces are conservative. And so the energy that can be stored in a spring can be put into our expression for conservation of mechanical energy. All right, in this question, we have, imagine it, you got a toy gun. I'm not going to draw it. But the toy gun, we can basically look at 3 different instances in time about what's going on inside the gun. And in one instant, we got a spring, and we put a projectile on it, and somehow you cock this thing, and the spring is compressed the most it's ever going to be compressed, right? We're loaded, and we somehow lock this thing there, and then in the next instant, we need to talk about, well, the spring goes back to natural length. Back to natural length, and the ball just loses contact. Yep, just loses contact, and is now moving the fastest it's ever going to move. We'll call that max speed. And then later, here's the spring still at its natural length. And here's the object up here at the highest it ever gets, max height. Come on, will you? Right? Good. And so there are energy transformations that happen the whole time. In the beginning, all we have in this system is elastic potential energy. Now, this is assuming that, let's call that zero height. All right? When we release this thing, pull the trigger, well, we turn that elastic potential energy into certainly KE, but notice a little bit, look at this. A little bit of GPE, right? This thing is currently above the height that we call zero. And then here that turns into, well, all GPE at max height, right? Max height's code word for velocity is zero. So energy transformations happen, all right? And here's what we can do. We can go initial to final. We can go initial to final. We can go initial to final. It's a question of really what does the problem ask? What do we know? What are we given? What do they want to know? So you got to choose where you're going to start analyzing and end. But those are the three instances you're going to have to use. Okay? All right. I'm going to shrinky dink. Good boy. Shrinky dink this stuff. Okay, part A, determine the spring constant. Oh, okay. Well, to me, what that means is we're definitely going to use this part. That's the only part where the spring's doing anything. And let's see, what do we know? Oh, here's what we know. Maximum height of 20 degrees above the 20 meters above the starting point. So what that says to me is, let's go here to here. I'll call this for A, initial to final. All right, we don't know what that speed is in the middle, so there's no way to talk about that middle part. So, okay, well, I'll start with this. We're going to assume, and a more appropriately phrased question would say, neglect any mechanical energy losses, neglect any friction between the projectile and the barrel of this toy gun, neglect any air resistance, blah, 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 blah. Okay? So I'd say, let's see, if I just, for the sake of being thorough, write them all out. Here's a big old expression for conservation of mechanical energy. As I've said before, and as I'll say again, please don't just write one kind of energy turns into another. All right? I've seen so far, it was really only one person in our last quiz did that, and guess what happened? They got the problem wrong. So don't do that. Start with the full expression. Now, based on where we've chosen our initial and final, here's what we can say. We can say in the beginning, well, we're at height 0. It's not moving. The thing is, quote, locked and loaded, right? At the end, springs at natural length, object's not moving at max height. So does this one turn into just two terms? That one kind of energy turns into another? Yes, it does. Does that always happen? No, it doesn't. So please be careful just saying GPE equals KE. Not always the case. We're looking for K here, so that's going to be K is 2 mgh divided by x squared. Okay. Or 2 times 20 grams times, I knew that was dumb to try. So equals, K equals 2 times 20 grams, but we want it in kilograms, times 9.8 meters per second per second. Final height, it tells us, is 20 meters above the starting point. That's our final height. X is how much the spring was compressed or stretched. Notice, the spring is compressed a distance of 0.12 meters. 0.120 meters. Don't forget to square. It's okay. It's okay. 2 times 0.12 times 9.8. Oops. Times 20 divided by 0.12 squared. Oh, I wrote this wrong. Anyone pick that out? 0.02 times 9.8 times 20 divided by 0.12 squared equals 544 newtons per meter. Yeah? It's okay? Oh, look, it did say neglect all resistive forces. Come on, who writes a good question? This guy. I didn't write this question. Speed of the projectile as it moves through the equilibrium position of the spring. Well, we want to know V. So we can go initial to final, or we can go initial to final. We have to include the middle part, where V is not 0. All right, I'd start with the same thing. Doesn't matter if we're gonna what we're gonna call initial and final, but over here. Why am I doing all this? I'm not doing all that. Delete. See ya. Get rid of those though. Come on. Come on. Thank you for your patience. All right, so in part B, here's the deal. Do you want to go from some EPE to some of each of these, or do you want to go from some of each of these to all that? The choice is yours, my friends. I'm going to do the second way, and you'll see why in a minute. So I'm going to go initial to final. And then I get rid of EPE in both cases because the spring has nothing to do with it. The spring's already literally done its work. And it's getting a max height. And I'm going to go like this. I'm going to say initial height is 0. But what I'm now saying is, for this part of the problem, I'm calling this 0. So this is no longer 20 meters, because that was 20 meters above this height. So it's now 20 meters minus, well, that was our x, the amount that the spring was compressed. So 20 meters minus 12 centimeters, that's 19.88 meters. I understand that's a little bit tricky. But it's nice that it allows us to turn this one into, well, yep, all the initial KE turns into all GPE in the end. I know I thought you said don't do that. Don't just assume that it's true. Okay? So 1/2 mv initial squared equals mgh final. Why did I choose to do this way? Well, because then we can do that. If you use the EPE, there's no mass in EPE, so you can't cancel masses out. This just ends up being a simpler solution to the GH final. Booyah. It's okay. Now, other kinds of questions, there are no models of these here, but, you know, you could certainly, for a simpler one, is this. You have a mass that's, you know, attached to a spring and compressed, and then the mass is released, and now this thing is moving at a speed v. And here we don't have to worry about GPEs at all, right? We turn all the EPE into all kinetic energy, right? So that's certainly a reasonable question to ask. You can do the opposite of that, where you have this spring just sitting there, and then here comes a mass, and what happens? Well, that ends up compressing the spring down to some maximum value, and you could find, you know, what that maximum value was. This would be all the KE turns into all EPE, right? If you're on horizontal surfaces, again, nothing to do with GPE, but you know, I would start them all the same way. As we know, springs exert conservative forces, so we can let's just start with the assumption that mechanical energy is conserved and see what terms stay and what terms go. Okay? Okay, folks. That is it, and that is all.